we're going to try to simulate a biped, and I'm trying to get to the point where I would basically simulate this robot here. Okay, so that's going to be the goal for today. Okay, so here's how we will proceed, which is we'll again download the template. It's called template_pendulum2.zip. It's on the shortened link tiny.cc MuJoCo. So download that, rename that to, let's say, biped, and make 3 changes. One, main.c, the make file, and then the run Unix or run Win depending on your operating system. And then if everything works fine, then if you run Unix or run Win, then you should see a pendulum being simulated. Once you get that, we'll modify that XML file and write code, which will get us to the point where we simulate a biped. Okay, so let me do that. Okay, so this is the template. Don't need this. Rename to biped. Okay, make 3 changes. So make file, change this to biped. The run Win or run Unix, depending on your OS. So this will change to biped. And then the main.c. Okay, so the main.c, we need to change this to biped. And then, let's also call this file as biped.xml instead of pendulum.xml. I'll need to make the corresponding change in the folder. So rename this file here as biped.xml. Okay, so we got that. Now let us see if this works fine. So navigate to this biped folder. Documents, MuJoCo, my project, biped. Okay, so that's the pendulum, which I believe we did this pendulum sometime back. I can open that file, and so it's set to be a floating base, X, Z in pin, and so I enforce the equality constraint, which ensures that the pendulum is hanging from the wall but not freely falling. Okay, so we modify this file now first in order to create the biped first. So let's see what's next. So a model of the biped is the one shown on the right. There are 2 legs, and what we'll do is we will connect the world to leg 1. So leg 1 is shown in green through 3 degrees of freedom, then X, Z, which helps it to move in the X and Z direction. But we also want that leg to rotate, so there'll be a Q1. And these 3 degrees of freedom are uncontrolled. You cannot control them. There won't be actuators controlling them. The leg 1 is connected to the foot through a knee joint, and that knee joint we would put a sliding joint L1, and that will help the leg 1 to retract, and foot 1 to retract, and that will help it to avoid scuffing the ground. Then on leg 1 we'll connect leg 2, and the way we connect leg 2 to leg 1 is through joint Q. I should have put Q2 here. This is not Q. This is incorrect. So that should be Q2. Okay, so that joint is actuated. It's the hip joint, and you can move it the way you want, and we put a position velocity servo there. And then leg 2 is connected to foot 2 through a sliding joint, and that is again serves the same purpose, to avoid foot scuffing. Okay, so we'll model this now in the XML file called biped.xml. Okay. Okay, so this is the state of the file now. It basically has the green link, as I showed you, that is leg1. It's already has X, Z, and pin. That those are actually the unactuated degrees of freedom. So we've already have this file in the configuration where we already have this thing set up. Now, what I want to do is, so leg1 is already set up and it's connected to the world using these 3 degrees of freedom. So what I'll do is now is add the foot to leg1, and then we'll continue adding leg2 and foot2. So let's just add the foot1 to leg1. Okay, so that's the next step. Okay, so we need to create a new body within leg1. Let's call that leg1. Well, that should be, sorry. I should name this as leg1. That is actually leg1. This should be foot1. Okay. And we don't need Euler. Let's see. So we need to, let's just put it at 0, 0, 0, and then we can move it around. Now, how does this foot1 connect to leg1? There is a joint, which is a sliding joint. So let's copy this. Sorry, the sliding joint should be this. And that joint is, well, when the leg is vertical, that sliding joint is along the Z axis. So I'm just copied the one for Z. Let's call that me1. It's a sliding joint. Let's worry about the position a little later. And the x-axis at 0, 0, 1. Okay. Now, we want to visualize this. So let's just put a sphere for the foot. So I'll copy this. It's called that sphere, and it needs only one dimension, which is the size. Let's make it slightly smaller than 0.05 is good enough, which is also the width of the cylinder. Color, that's green. Let's make the thing, I think this comes out to something like yellow. And we want to make the foot very light. So let's just make that 0.1, which is 1/10 of the mass of the leg. Okay, I need to close this bracket for body. So that's it. Okay, I think we are best served if we are using the simulate to actually build this model, as we've always done before. So instead of running the main file Unix, I'm going to navigate one level down, go to 2 levels down, sorry, go to bin, and then simulate. Okay. There's an error. Unknown element pole. Okay, this is because I renamed the pole, and then there was an actuator, I think. So there was an actuator for, there was an equality for pole. Okay, so I just have to get rid of this because I will not have this constraint eventually. So let's get rid of that. Now reload. Oh, I cannot reload. Let me try putting it down. Okay, it fell down, no wonder, because there is nothing holding the pendulum upright, but we couldn't really see the foot. So what I'm going to do is a few things. First of all, change gravity and make it 0, 0, 0. Now reload. Okay, I just can't even see the sphere, and I think it's because it's right here, it's embedded. So one way to do that, to see the sphere, is we can reduce the transparency of the leg. So we can do it right here. This is set to being opaque. Let's make it 0.2. Okay, now you can see the sphere. It's right in the middle. Now we should turn on the visualization for the joints because we are also creating joint positions. So let's open, well, it should be in rendering. Rendering is here. So we'll make it show the joints. Okay, so here it is. So X is to the right, Z is up, and this is theta. And you can see that this is a joint which we define. It's upward because we said 0, 0, 1. And then the sphere is sitting right here. So what we want to do here is perhaps move this down, and we need to decide how big, how much clearance we want. So this distance is 0.5, and I want to perhaps move it to 0.75. So I'm going to move it, the sphere, 0.75 down. So I go to sphere and I say minus 0.75, and then let's reload. Okay, so now it's at 0.75, but I want to perhaps define the axis that's downwards and not upwards. That is for the sliding joint. So let me change this to axis minus. Okay. Okay, so that looks better. So we have now created the leg. And since this all looks good, I'm just going to get back the transparency to being opaque. So this. It's a little odd that the axis of the sphere are sitting right here. Maybe I want the axis right at the tip of the cylinder. So right now it is set to 0, 0, 0. Okay, but I want it to move up. And remember that this distance is 0.75. So if I want to move it up, I want to probably move it by negative 0.25 because that distance is relative to this point first. And then the other thing is that since the positive axis is downwards, so it's a local axis, I need to do negative and not positive. So let's try minus 5 for the joint. Oh, my bad. So it should be positive. Yeah, my bad. The axes are still positive Z's upward. So that looks good. Okay, so we've created, let's see, our plan. We've created the foot 1. Now let's create leg 2. And leg 2 is connected to leg 1 through Q2. So there is a pin joint. Okay, so what's the easiest way to do this? Well, there's a pin, but I first need to define the body. And remember that this leg 2 is attached to leg 1. It's at the same level as foot 1. So I should not create this within this body. I need to create it outside, because otherwise, if I create it within this body, it will be part of foot 1, but I want it to be part of leg 1. So I need to create it right at this level, at the same level as foot. So body, and we'll call it leg 2. Oh, sorry, it should be like this. Let's put it at 0, 0, 0. And then let's define the sliding joint for this. Sorry, the pin joint for this. And remember that the pin joint, we'll call it hip because that's the hip joint. And let's just put it at 0, 0, 0. And then axis look right. It's about the z-axis. And I think if I just do this, it might give an error because I've not specified the mass. So let's copy paste this part, which gives me the leg. It shows basically draws a leg for me. And so that would be cylinder size is okay. RGBA mass is 1. RGB. I'm going to change the color just to suit this one. It needs to be gray, and gray is 0.9, 0.9, 0.9. Okay, now let's try to see what we get. Okay, so what happened here was the green appeared, so the gray appeared on the same place where the green was, and that's not what we want. So what we want to perhaps do is we want to separate these legs out along the lateral direction, along the third direction, so along this axis or the y-axis. So the simplest way to do that is, we have a choice. We can move one of the legs or both of the legs by the same distance. So let's say that we just move the one leg, it's easier. So along the y-axis, move this by 0.25, and that is basically corresponds to the width of the hip. It's the distance along the lateral directions. Let's load. Okay, now it's come out. Okay, we've got that. Now, what I want to do is I want to move this slide, the hip joint right here. Right now, it's in the center of mass. So I clearly need to move it up by a distance of 0.5 because it's basically the center. So I believe I need to put positive 0.5 for here. Okay, there it is. Okay, looks good. Okay, so I've achieved, I've been able to create the leg 2. Now let's move on to the foot 2. So the foot 2 is connect leg 2 through the sliding down L2. It's essentially, it would be taking this code for leg 1, foot 1, and then pasting it for foot 2 and just renaming things. So let's do that. That's the easiest way. So let's take this code in its entirety for foot 1. This would be a part of leg 2. So I would make it inside this body for leg 2. It should be this. This just is for the readability that they are aligned. So foot 2, knee 2. I believe that I don't need to do more changes. It should work. Let's see what happens. There it is. So looks good. Yeah, I think we've modeled the biped now. Okay, I would say that we can proceed, but why don't we just define the actuators? So we just do the actuators, and then I don't think we need to touch this anymore. So right now, if you see here control, there are no actuators. Well, there are two actuators, position servo and velocity servo. What we will do here is we'll add a position and velocity servo for the hip. We'll add a position and velocity servo for foot 1 and foot 2, or the knee 1 and knee 2. Okay, so let's do that. So right here, this joint, right now the servo is for pin, but we know that the pin, that's really an unactuated joint. So it needs to be put to the hip. So let's just change that to hip, hip. And then we can just set some random values, and we can always change them to 0. So 110. So it's for, let's call that P servo hip, P servo hip, okay, P servo 1, P servo knee 1. This will be joint knee 1, knee 1, okay, and then the P servo knee 2, V servo knee 2, knee 2. Now let's reload. Yes, you see all these actuators came. We can move and just check if this works fine. So this is the servo for foot, moving out and go in and move the hip. Okay, looks good. Okay, so I think this simulate has served its purpose. Let's quit it. Navigate back to my project. So my project, and then bin, and then run mix. Didn't quite go in the folder. CD project, biped, and then clear the screen, run. Okay. Okay, if you want to change the view, I think here we might be better served by changing the view to this. This is how I do it. I already have put the code to do that. So you need to go navigate down here, go to the place where I've defined cam dot bunch of variables. So cam here. What you want to do here is it's right here, it's in printf. So uncomment this line of the code 304, run it, change the orientation to whatever you want. So let's say this is better, I think it's good. And then it will actually print out this configuration, this viewpoint. And so take this and comment this, we don't need it anymore. And change this here. So I'll keep that one because we might need it later on. Copy paste. Okay, and now when you run this, you'll see that it will give you that view. Okay, so we've done one part, which is created the model. Let's move on. Okay, so before we do any control, we need state estimation. And why I say state estimation is there's no noise here, but there are things which we want and they are not readily available in MuJoCo. So we need to make some effort to define them. And so that once we define them, we create variables for them, we can then use them in our simulation. There are two things I think are important. One is we want to figure out the absolute angle of the leg. So this is leg 1, it makes an angle with the vertical, okay, not with the leg 2, but just with the vertical. And we want to compute that and keep that saved because we'll need it in the state machine. We also need the absolute angle of leg 2. This angles comes from, and I'll show you how to get them from basically what MuJoCo does is it basically gives you the orientation of the leg with respect to, or sorry, the body with respect to the world frame. And that basically, that information is available as a quaternion, and you need to convert that quaternion into an angle. I have some code which will do that for you. And once that angle is there, we can then use it in the controller. There's another relative angle between the legs, and that is precisely the hip angle. So that is readily available. We don't really need to worry too much about it. We will see that if the leg 2 is in front, this angle is positive, and if it's behind, the gray is behind, it's negative. We would also need the position of the foot, and we only need that because we want to figure out when the foot touches the ground so that we can switch the controllers. So we need the Z position of the foot, and we need the absolute angles of each of the legs because they will be used in the next stage. So first step would be to get these angles. Okay. Okay, so let's do that. Let's get the angle. Before we set the angles, let's just, I'm going to put a random angle for the control, for the actuator, so that this leg is not parallel, but it is at an angle not equal to 0. So I'm just going to move the gray leg or leg 2 by an angle. And once we have that, then we can start writing the code, because then we have a good way to figure out what, we know that the absolute angle is not 0, and that it'll be easier to code it. So what we'll do is we'll work here with init controller right here. We'll initialize the controller. So in this case, first let's initialize the position of the hip. And something which I forgot to do was, and I just occurred to me, is maybe I should have got the model.txt file from simulate, because we would need that in order to figure out these things. So I'm going to just do that right away. So let's go back to bin cd. This is fine. So cd cd bin simulate. Just drop biped.xml. Okay. We go here, print model. Then go back to bin. So that would be MuJoCo bin. And you can see this mg model.txt, it was just created. So let's copy this and put that in Biped. Okay, we need it. Okay, so we don't need this anymore. Quit. We get one level up. We get 2 levels down. Okay, so we are back to this place now. let's do what we were just about to do, which is set the initial position. Now, when you want to set the position, we want to set, let's see, we want to count the angle. So this is the first degree of freedom is that of the zeroth one. So I'm talking about the degrees of freedom of the system. So there are three unactuated degrees of freedom, X, Z, and pin. And here I'm trying to set the hip position. So 0, 1, 2. The next one is 3. 3 is knee. And then fourth one is the hip. So I need to set the hip to whatever I want to. So it'll be the fourth one would be, let's just set it to 0.5. Okay, now setting that will set the position, initial position. But remember, we already put a spring here, and the spring has a set point of 0, which means that it will spring back to the position where legs are parallel. So I also need to set the controller. So it's DCTRL, and I need to choose which. So I need to put the position servo on. So this would be correspond to, in the actuators, the position servo for the hip joint. So that is the actuator number 0. So I need to put 0 equals either 0.5 or you could just put Q pose for that. Okay, so let's run this. Okay, so there it is. It's the leg is in front, and this is what I expected. Now, once we got that, now let's try to work on state estimation. So we'll try to get all these angles. Okay, so I'm going to do some work and make my life easy. I always like to, define all these variables of interest, which is we have X, Z, pin, and so on. So we just define them. So X equals the Q pose 0. I'm just defining this because I want them in a way that I can use them. And so instead of trying to define them later on as a need basis, I'm just going to create them here so that if I need to use them, I can just pull them as a variable. So double X equals that, double Px equals the QVal 0. So that's the position and velocity of the slider joint along X. And I just have to copy this. It'll be Z1, VZ1. So after that is the pin joint, and we've defined that as Q1. So let's call that Q1. Let's call that U1, Q2. Okay, after this comes the knee joint. So let's define that as, I think I've defined it as L1 and L2. So L1 is what I'm after. L1 is the next joint after pin. L1, let's call it L1 dot 4. Should be 2, 3, 3. Okay, after L1 is hip. So that's Q2, Q2. Let's take this. Q2, 4, 2, 4. And then finally we have L2. So okay, 0 through 5. Okay, so this is just not needed in this code, but I just thought I'll define them so if you need it, we can use it. Okay, now let's get to this point where we're figuring out the absolute position of the legs. Now, the way this is done, as I said in MuJoCo, is it gives you the quaternion. So let's open the XML API reference. Okay, so here just search for quaternions. Or quat. It's where Q poses. This is what I wanted. So, what is familiar here? Let's see. Yeah, Q pose, not this Q pose. There's another Q pose. Body pose, body quat. Okay, what I want here is I can't quite find Q pose here. It's probably somewhere in somewhere on this page. So what I need here is the quaternions, and I'm just trying to find the right quaternion to use. There's a body quat. Q pose. Body pose. Body quaternion. Okay, so this one will give me orientation of one body relative to the parent body, which is not what I want. I really want the absolute angles eventually. So I need the quaternion for the leg or the body with respect to the world frame. This is not it. I quad, that's for orientation. It's not the one. Oh, maybe it's here. MJ data, Q pose, Q well, we've used those. CTRL, we've seen that before. Yeah, that's the one I'm looking for. So Cartesian orientation of the body frame. So it gives you the orientation of the body with respect to the world frame. Okay, so it's the keyword here is Cartesian. That means it's with respect to the world frame. And it's basically 4 numbers. In fact, the way the quaternions are is that there's one number which is a constant, the first one, and the negative, the remaining 3 are gives you the non-constant part, so qx, qy, I call that qx, qy, qz. So what I'm going to write here is some code which will essentially take the quaternion and convert that to Euler angles. So it will give me 3 angles, and those correspond to orientation about the x-axis, y-axis, and z-axis. So what I've done here is I have a function here called utility.c. It is a function which converts bunch of transformations. So the way you can write orientation is you can write it using direction cosines. So that would be mat. You can write it using Euler angles. So if you have direction cosines and you want to convert to Euler angles, then you use this function. If you have direction cosines and you want to convert to quaternions, then you use this function, and so on. So Euler to mat, quad to mat, and Euler to quad, and quad to Euler. There are 3 representations: quaternions, Euler angles, and direction cosines. And this utility will basically give you any conversion you want. So what I'm going to do is extract the quaternion using that command I showed you, or that variable I showed you in MuJoCo, and then convert that to Euler angles. So I'll have to use quat to Euler. Okay, so I'm just going to take this. This is the syntax I need. Let's go here and just call this part state estimation. I'm going to use this. Okay, but before I use this, let me first pull out the orientation of the leg. Okay, so I'm here. In this case, I'm interested in the orientation of leg 1 and orientation of leg 2. So let's see how to get that. So the way this is you point to D and then you get X quat. And remember that it is, where is the documentation? It's n body times 4. So the best way to get that is, it will be if you define a variable called, let's call it here, int body number, then it would be 4 times body number. So if you want to find the constant part, let's call that q quad 0, then it will be 4 times body, where of course you need to specify the body number. So if you specify the body number for the leg, it will give you the constant part, the first one. Then you just keep doing that. Quad x, that would be +1. Quad y will be +2. And then quad z will be 3. Now I've not defined these. Let's define them right here. Double quad 0, quad x, quad y, quad z. Okay, so I've now saved them. I need to specify the body number. This is where I need to use that MJ model file. So if you open the MJ model file, this is what it looks like. As I said, I'm interested in the leg 1 body number. So I just scroll down. So body 1 is leg 1. So if I put body number equals 1, then I would be on leg 1 and give you the orientation of leg 1. So I just say body is 1. And I can print this, but those quaternions won't make any sense to me. So what I'm going to do is I'm just going to convert that to Euler angles, and then maybe it'll make more sense. So I'm going to call this function. So I need to call E4. So this is the constant part. This should be the x, should be y, should be the z. Okay, and now I need to pass pointers to the Euler angle. So let me define some Euler angles. Double Euler x, Euler. So this will be pointer. So and Euler x ampersand y ampersand Euler z. Okay, so now I can print this. So printf body equals %d angles equals %f line. So this will be this will be the body number. So it will be body number x, Euler y, Euler z. Okay, so everything worked right. It will give me angles in gradients. So let's do that. Okay. Okay, did not find quad 2 Euler. Okay, so I'm calling a function here and doesn't know that this exists. So what I need to do is I need to define this utility.c and it tell the compiler that look into utility.c. So I need to go up here and add this utility.c. Should work now. Yes, so it's stationary. You can see the Euler. So body 1 is leg 1 green and it's standing upright, and I don't expect the Euler angles to be any different from this. So this looks good. Let's try to do this with second, the body, the leg 2, and then see if that changes, because we know that's not aligned along gravity direction. So let's, good thing about this is you can just copy paste this code. Body, okay, I don't know the body number for leg 2, but if I go in the MJ model.txt, so body 1 is leg 1, body 2 is foot. I don't want the orientation of the foot. Body 3 is leg 2, so I'll just use 3. And let's see what this prints. It printed 0, 0, 0, and that's because I should propagate the equations, right? So this is not really, it's just initializing the controller, but it's not really doing MJ forward here. So the number of ways to fix this, you could call MJ forward here, it'll fix that. Let's just try that first. MJ forward. TM. So after setting the angle and control, I did MJ forward. Then it updates all these data data structure, and then now I think it should be okay. Segmentation fault. I think it's M comma D. There it is, minus 0.5, which corresponds to this angle of the second leg. Okay. So that's one way to do it. The other way to do it, anyway, this code won't be sitting here. It will be sitting in my controller. So what I'm going to do is, why take the pains of defining all this here? So I am going to take this part, all this part, in fact. So I remember I commented out MJ forward, it's not used. Let's take all this. And why is this happening? I need to get this whole thing. Okay, so we got that. Let's move it right here. Okay, now this part we know is called every whatever time integration time step. So this one will set the initial position, but this one will print it. So this is executed in my MJ step, so it's already in. So we don't need to call MJ forward. Let's just see what this gives. It'll actually continuously print the values. It's no surprise it's printing continuously. You can see that body 3 is minus 0.5, and minus 0.5 corresponds to the gray leg or the leg 2 being forward. Now, just to make our life simple, what we'll do is we'll stick to this convention that if leg 2 is in front, it's positive angle. It's just a preference. You can stick with that. So all I'm going to do is I'm just going to interpret the negative as positive in order to do that. So double apps leg 1, apps leg 2, and then I'll just apps leg 2 equals minus Euler y. Okay, so remember that these Euler x and Euler z are 0, but Euler y is not 0, and that's because we are rotating about the y-axis, and so x and z, the orientation with respect to x and z doesn't change, and so we'll only see that for a planar system there'll be only rotation about one axis, and that is the one we care about. So let's make it apps leg 2 is negative Euler y, just so that it gives me positives forward, and I can do the same thing for leg 1. So that would be Euler y for leg 1, and then I don't want it to print. Okay, so this completes one part of the state estimation, giving the absolute angle. I also need the position of the foot, and that's something we've done in the past, especially in the Hopper lecture. So in order to get the foot position, I need to use DQ pose, right? And if you look at the documentation, my bad, X pose is what you want to use. X pose with the Cartesian position of the body frame. It is n body plus 3. So again, if I need the X position, it will be that 3 times body number plus 0. So I don't get that. Y equals T equals 3 times body number plus 1. And then Z equals T equals 3 times body number. This is going to conflict with these X, Y, Z. So let me just define them as we don't really care. So we are only interested in Z position. So let me just not even bother with this. Let's call this position Z or Z foot 1. Okay, so if I want to position the Z position of foot 1, I need to figure out what that body number is. So again, this is where I need that MJ model file. So foot 1 is body 2. So body 2. And then we can print F line Z foot 1, but this will give an error because I've not defined z foot. So let me just define z foot. In fact, let me just define double z foot 1 and z foot 2, which I'll use for z position of foot 2. Okay, this should be exposed, not z pose. So let's run this and see if it compiles fine. Okay, now it's in 1.25. I pretty much want to figure out when it hits the floor. So what I'm going to do is I'm going to turn the gravity on so that it will fall, and whenever it hits the ground, I'll know exactly what the foot position is when it hits the ground. My expectation is that the position of the z foot when it hits the ground is equal to the radius of the foot, which is 0.05, and we'll see that. Okay, so what I can do is I can set gravity here, but I'm going to show you how to set gravity in the code. So to set gravity in the code, you can actually turn on and turn off the gravity as you want. Let's just put it right here. So I'm going to turn gravity on, what you need to do is you write this. You use this model structure. It's actually in the model. It's called opt.gravity. Okay, so that's the it's within the model structure. So m opt.gravity. And so there is x, y, and z components. Since we're only interested in the z component, I'll just put that equals minus 9.881. Okay, and then you see that it'll actually fall in the floor. There it is. Okay, so it fell on the floor. It made us take a sort of a step. And then you see that it's 0.049, which is the z position of the foot, which makes sense. It should be about 0.05, right? Because that's the radius of the sphere. Okay, so this looks right. So I can just now go here and copy this. I need to get the foot 2 position. So if you go and look at the MJ model file, body 4 is foot 2. So 4, it's foot 2, and to print this. Okay. So now it gives me position of foot 2. Now this, you saw that it fell from a height of, I think it has specified a height of 2 feet. It fell from a height of 2 meters, but the length of the leg is 1 meter. So what I need to do is, let me move this whole thing down a little bit so it doesn't really fall from the air. So in order to do that, let me just for a second. It's okay. Okay. So this length is 0.5, and this length is 0.25, the foot. And when I'm setting this position of the position here, this is basically setting the position of the center of mass of leg 2. In other words, that position corresponds to this point, leg 1, right? So in order to put that at the right distance from the floor, I need to compute the distance in the z direction when it's vertically upright from here all the way to the foot. So that will be 0.5 and 0.25. Right? So I'll just try 0.75. Okay, let's see what happens. Okay, that looks fine. Okay, so 0.75 is good. So it's now just started right in the middle. But look at it one. Yeah, it looks fine to me. Let's just keep it that way. Let's print this just to be sure. Yeah, it's fine. 0.49 again. Okay, so I think we have come to the point where we have set this, set the robot and got state estimates. Now, what we're interested in this is we're trying to simulate a robot which walks downhill. Okay, in order to simulate a robot walking downhill, one option is to turn the plane to be at whatever angle we want it to be. that is hard to do in this. So what we'll do is instead we'll turn gravity vector so that the gravity vector, instead of being vertically down, is actually pointing at an angle, whatever that slope angle, angle of the slope is. And so the component of the gravity in the x direction will be g sine of, let's call gamma is the angle of the ramp. So d sine gamma, and then the vertical component will be d cosine gamma. So I'll just make that change right away first, and then we'll move on. So go to main.c where we define gravity. It's called double 9.81. And I need to set the x component to be gravity times, as I said, it should be cosine of, we need to specify the ramp slope, that gamma equal 11.1 slope, and then m, so it should be negative. Gravity, this will be the x component because it's moving in the xz plane, so 0 equals gravity times sine. I don't think that will cause any changes in the visualization. Yeah, it's actually fair. Okay. So we've got that. Okay, I think we are ready to do the control code. So let's see control part. Okay, we got this state machine. Okay, so the way I'm going to do this is I'm going to have 3 state machines, 1 state machine for the hip, 1 state machine for the foot 1, and 1 for the foot 2, or rather 1 for the different joints. So hip, knee 1, and knee 2. Okay, so here's my logic for the hip state machine. I'm just going to have 2 states. The first, in the first state, let's say that I'm going to start the robot in this state, in leg 2 swing. So in this case, leg 1 is on the ground, as we've seen. We've already put leg 1 on the ground. Leg 2 was up in the air. So leg 2 will be allowed to swing, and we'll try to get the leg 2 to do position control. So we want to try to for the leg 2 to be at an angle of 0.5, and now 0.5 happens to be front, right? As I said, relative angle positive is leg 2 is in front. Okay, and that I found out by doing the same thing, which is visualize, putting an angle and visualizing it with that, just like I did it some time back for the absolute angle. Okay, so it's going to set the position to be 0.5, and then when the leg 2 hits the ground, okay, how do I know the foot has hit the ground? Well, I look at the z position of the foot. I also need to ensure that leg 1 is negative, or vice versa, if leg 2 is positive, to be sure that leg 2 is in front of leg 1. So that check ensures that one is in front of the other. So once I have these 2 checks are met, I'm going to transition to leg 1 swing. So now leg 2 is on the ground, leg 1 is swinging. And since the leg 1 is swinging, and I'm setting the relative angle to minus 0.5, which is telling the leg 1 to go in front, right? Relative angle is negative when leg 1 is in front. And then again, I wait till leg 1 touches the ground. Again, there'll be 2 conditions. One is foot 1 is on the ground, so the z position of the foot, and then the absolute position of the leg 2 is negative, or absolute position of leg 1 is positive. Either one will do it. So that's the state machine for the hip. So I need to program the transition conditions, and then the transition conditions are the ones in red. And then I need to program the actual commands in the state. So that would be this one. So I just have to set the position. It's pretty simple. Just have to set the control corresponding to the position server to be 0.5 and minus 0.5. Okay, for you know what, let's just program this, though we will not be able to check this because unless the robot walks, we cannot check, but let's just program this first. Okay, let's programming this. Slip it to the side. Okay, so all transitions here, all actions here. I think it's super easy to program the actions, but first let's just find the state machine. So I would like to make them global variables. So int FSM, I think I call them FSM hip. Hip. I need to define the state. So define FSM, let's call that leg1 swing, or leg, doesn't really matter if you can call either one 0 or 1. Define FSM leg2 swing. I think that's it. Okay, now I need to initialize the FSM. So go to init controller. Okay, now to initialize, remember that I start the system in such a way that leg1 is on the ground and leg2 is in front, which means that I've set the hip to be in leg2 swing. So initialization is FSM hip equals FSM leg2 swing. So initialized. Let's go to transitions. The things in red. So if so first of all, I need to check if FSM hip equals FSM leg2 swing. So we are here, and Z put to so remember it was 0.05. So let's just make it 0.049. So 0.05 is a good trigger. And as I said, leg1, absolute leg1 is negative. So abs leg1, which I've already defined here, is less than 0. Then I want you to transition to FSM leg1 swing. That's all. Then if FSM leg hip is in FSM leg1 swing, and then Z foot 1 is less than 0.05, and absolute leg2 is negative, then I want to transition FSM leg2 swing. Okay, that's done. Now let's give the actions here. FSM hip equals FSM leg1 swing. Okay, so if you have an FSM leg1 swing, I want you to set the control CTRL corresponding to that actuated so position servo to be minus 0.5. We've seen that that corresponds to this one. This is the hip, the position servo, so it's CTRL 0. So D CTRL 0 equals minus 0.5. And then this should be 0.5. So I'm just going to take this. Leg2 swim is 0.5. Okay, so that is completes the state machine, though I cannot test it because if I run it, there's no clearance. It's not going to go anywhere. So I'm just not going to try to test it. Okay, so let's do this let's look at the knee state machine. Okay, so we're going to consider just two phases in the knee state machine. There's going to be a stance and there's going to be retract. The stance is when the leg is fully extended, or L1 is 0. And retract is when the leg is shortened by 0.25, and that is to do ground clearance. So let's say that leg 1, we're starting the leg 1 within the ground. So it's going to be in stance 1. And leg 2 is, let's say it's in stance 1. What I need to do is I want to retract leg 1, but I retract leg 1 only when leg 2 is on the ground. So what I do is I check if foot 2 is on the ground, this one, and leg 1 is trailing leg, so absolute angle of leg 1 is negative. You could also check absolute angle of leg 2 is positive. That'll be just fine. If that happens, then I want to transition to retract, which means that leg 1 retracts now. This should be, sorry, it should be minus 0.25, not should not be minus 0.5. So it retracts, and then the leg will swing because the hip state machine is making it swing. And then at some point when it is, so it clears the ground, it doesn't scuff. And then once the leg 1 is in front, at some leg 1 angle, some positive leg 1 angle, because forward is positive, I want it to go back to 0. And then you go to stance phase 1. So the transitions are in red and the actions are in the bubbles. So I'm just going to program that next. So when I'm starting the state machine, remember that leg 1 is in the stance phase because leg 1 is in the ground, leg 2 is in the air. So I need to start in this phase. So let's do that. So next state machine is FSM 1. I define 2 states. Some knee 1 stance. Let's call that 0. FSM knee 1 retract. Let's call that 1. Okay. Now let's go to init controller. As I said, we start in the stance phase. So FSM knee 1 equals FSM knee 1 stance. So it's set in this phase. Let's go still down and define the state machine here. If FSM knee 1 equals FSM knee 1 stance and okay, so we're in this state. Well, we want to transition to that retract phase. We check these conditions. So Z put 2 is less than 0.05 and abs leg 1 is trailing, so it's negative. In that case, we want to transition from FSM knee 1 stance to FSM knee 1 retract. Okay. And then the next transition is from retract to stance is when this condition is met. So if FSM knee 1 equals FSM knee 1 retract and abs leg 1 is greater than, I mean, you could put 0, but I think to be safe, you want to put some greater than 0, something like 0.1 or 0.05. So FSM knee 1 equals FSM knee 1 stance. Okay, so it goes back, and that's it. Okay, so this is the state machine. Let's do the actions. If FSM knee 1 equals FSM knee 1 stance. So if it's in stance, you need to set L1 equals 0. So what is L1? Let's go to here. So we are trying to set the position servo. So this is the third actuator. So 0, 1, 2. So it will be CTRL2. So D CTRL2 equals knee is 0. And then FSM knee retract. And we should set this to minus 0.5. Okay, I think that's about it. We've set the state machine for we have set the state machine for the knee 1. Okay, now knee 2 is exactly the same as knee 1 except in reverse. So you just the logic just changes. So I just need to swap out 1 to 2 and it's the same. So I'm not going to re-explain that. I'm just going to code it up. This should be 0.5 as I said. Okay, let's just code this up. So I'm just going to do a lot of copy paste here. It's much easier to do it that way. Okay, so we need to define FSM knee 2. And then this would be again 2. Okay, now I need to initialize this state machine. So remember that the leg 1, when this starts off, leg 1 is on the ground and leg 2 is in the air, and it's probably leg 1 is probably greater than 0.01, which means that leg 2 should be in stance phase ready for touchdown. So what I'm going to do is I'm going to initialize this in the stance phase. This takes care of that. And now I go here and state the state machines. Copy this, paste. Okay, so need to. Okay, so I'm in the stance phase. I need to transition to retract. I check for Z foot 1, apps leg 2. 2 goes to need to retract. Then need to, if I want to transition from retract to stance. So retract to stance. The leg 2 should be greater than 0.1. 2 should be this. So that takes care of all the state transitions. Let's go here. Okay. Now I just need to find what this CTRL is. So if you go to XML, it's the position servo for NE2. That would be 0, 1, 2, 3, 4th actuator. So put that as 4, 4, but this should be for NE2. Okay, I think I finished programming the entire state machine. So now it's time to try to run this and see if it works. Okay, so there is, you can see that it's wobbling. Okay, so the leg gets buried in the ground. So it's probably because I don't have a high enough servo here. Just try to put 100,000. So this is going back to our hopper where there was not enough P gain, and that's why it started wobbling. I'm guessing that's the issue based on the evidence from the video. Okay, so it took a step but went back. Let me try again. Also, it doesn't look like it really swung its leg in front. I wonder why that happened.
I don't know. I think
Let's
there
try
are some
to increase
errors.
gravity because gravity helps it to propel in front. So go. Gravity, and so I'm just going to increase the ramp slope to 0.2 and see if that helps it.
Professor.
So there is a problem with the
you,
leg not swinging in front. That's clearly the problem. It's went forward. Now the green leg or the leg 1 didn't swing in front. So we need to figure out why that's happening. Okay, so it's probably here. Either the FSM didn't transition or it is something else. Okay. I'm just trying to think what could be there. We could, well, this is right. Okay, 0. That's right. Okay. In the actions, you define something in the transition for stance to retract need to. Interesting. Let's see that. Let's see this need to. Okay, let's look at this. Foot 1 on ground, leg 1 is negative. Okay, there's an error there. And then leg 2 is positive. Then what about this one? This foot 2 is on the ground and leg 1 is trailing. leg 1 is, oh, leg this is also wrong. Leg 2 is trailing. So foot 2, so see, foot 2 is on the ground and leg 1 is trailing. Right? And then foot 1 is on the ground, leg 2 is trailing. Foot 1 is on the ground, leg 2 is trailing. This is right. It's leg 1, leg 2, leg 1, leg 2. 255. Oh, this right. This shouldn't be equal to. Maybe that will. I don't know. Let's see. Yeah, it works. It just went pretty fast. It'll probably fall. Let me, it's just hard to debug this way. Let's do a few things. Let me increase the ramp size. Let's make it, use the ramp size, ramp plane. So let's make it 1,000 along the x-axis. Okay. The other thing is let's move the camera with the robot. So to do that, we go in here, cam, look at cam dot look at, and then we make this correspond to the x degree of freedom. That's how it moves. So q pose 0. Okay, there it was. I think these gains are too high. Just go here and let's write 10 and 1. That sort of works, not that great. Let's just change. What I'm trying to do is I'm trying to tune the frequency so it's not very, so if you try 10, this will probably work. So we did that, but I would just change the ramp slope a little bit because I think I just changed it to 0.2. It's just been to 0.1 and see if that's the problem. It's going too fast because of the ramp slope. Just change it to 0.1 and then see if that does it better. So here what's happening is a very stiff controller. So you can see it's just moving the feet so fast. Okay, I'm going to increase the time. Let's make it see 25 seconds maybe. That's too short, too long. 20 seconds good. If it doesn't fall for 20, it probably won't fall forever. So you can see that the PD controller is so stiff that it is going, it's sort of going, it's very energetic. It doesn't really look natural. Yeah, so it just works. So I think that will work. Now, as I said, it's not natural. And the reason why it's so looks energetic and so stiff is because of the hip controller. So I have a very high gain on the hip controller. So what I'm going to do is I'm going to modify the gains and just sort of tune the gains so that it looks natural. It doesn't really look like it's so stiff. So let's play with the gains for the hip controller. Okay, let's try, as I said, I tried 10 and 1. It looks like it sort of works. So you can see that this is what is known as a period 2 gait or a sort of drunk gait where it takes a big step in one leg and then takes a short step. This is actually, if you know a little bit about chaotic solutions and chaos, this is basically means that you're very close to the vicinity of a good solution. It's just that you need to tune the numbers so that you get a symmetric gate and not this asymmetric gate. So what I'm going to do is I'm just going to play with this. Let's try 8 and 1. Still is period 2 or the truncate. Okay, we can try, since it works, let's try 6. I think it's getting better. Let's decrease it to 4. Let me just print the step number. I think it's fun to see as it makes progress during the step. So I'm just going to create a variable for step number, int step number, initialize the step number to, so the goal is to count the number of steps before it fails, or it may not even fail. We don't know that. So step number equals 0. And every time it hits the ground, I need to initialize the state machine. So the best way to do it is probably here. So step number plus equals 1, printf step number equals %d, new line, step number. Okay, I just need to, so this is one step, and this will be another step. And so we can do is see how far it goes before it falls. I would try, how much time we have? Let's do 60 seconds. Okay, so it took 89 steps, didn't fail. You can try this for longer time period and see if how it does. But